Hello friends, welcome to my channel. Let's have a look at problem 1627 together. Graph connectivity with threshold. In this video, we are going to share a solution based on disjoint set data structure, also known as UniFind. This problem is marked hard in Leetcode. However, if we carefully analyze the statement or the logic in the problem, we can come up with a very short solution. So this problem asks us to return an array called answer, where the length of answer equals to that of the queries, and answer I is true if for the ith query there is a path connecting the two nodes in that query. So the condition for two cities to be directly connected is that there is a common divisor for x and y that is strictly larger than some given threshold. So this condition actually is equivalent to the following statement. So x and y are directly connected if and only if their greatest common divisor is larger than the threshold value. So this is the main statement or logic in this problem. So here are three examples given. We are not going to go over the three examples now. So after we analyze the problem, you are encouraged to walk through all the examples. So now let's look at the constraint for this problem. The first constraint is about the number of cities, which can be up to an order 10 to the power 4. So 10 to the power 4 is a decent large number. So when we devise a solution, we need to take Temp complexity into consideration. The second constraint is about the threshold, which is less or equal than n, as it should be. So the final two constraints is about the queries. So in each query, the two cities are different. So this is more or less a consistency assumption. With that said, let's look at the method. So as we mentioned, we're going to give a solution based on disjoint set data structure. So the idea is actually very routine. We're going to use disjoint set data structure to build clusters, and within a cluster, two nodes are connected. So this idea is listed here. However, a question arises. So how to effectively do union operations in this problem? We cannot do it in a purely brute force way. So let's recall, two cities x and y can be connected if and only if their greatest common divisor is strictly larger than the given threshold. So we are going to do the union using the following nested for loops. So due to the requirement from this problem, we are going to look at the threshold value that is larger than the given threshold. So we are going to iterate for a city x, let's see, in the range threshold plus 1 upwards. And then when we look at another city, we're going to just look at the multiples of city x. So this way, we're iterating like in range 2 times x up to n with a step x. So here we start from 2 times x, means that we do not need to check y equals x. So this way, actually, it can accelerate the connectivity procedure or merge procedure effectively. So this is the reason, because we are looking at multiples of city y, multiples of city x at y equals kx. Then this way, the greatest common divisor equals x, which is larger than the threshold. So with the key idea explained, let's specify our plan. So first, I'm going to implement the UniFind inside the solution function. The reason we choose this kind of implementation is that the number of cities is given a priori. So in general, we can actually implement the UniFind as a separate class outside the solution class. So secondly, we're going to do a coarse temp complexity analysis after we solving the problem. So here are some initializations. So in order to implement the disjoint set data structure, we initialize two dictionaries. One is parents, one is recs. The parents will store the node parent relationships, and the recs will store the node and the rec relationships or the information. So this is the initialization. At the very beginning, each node or each city is a single node cluster. So its parent is itself and its rank is 1. So next, we're going to define the find function. So for this, the find function accepts one argument. This I is the city or the node. So like 1, 2, up to n in this problem setting. So this is a very routine to implement, but I'll choose to implement with path compression. So let's introduce a temporary variable called result. Its state is I. We're going to return the final state of the result. So next basically is a while loop. So result, if the result does not equal to the parents of the result, then we're going to update the result to be its parents. Then after we exit this while loop, we're going to return this result. So that's the standard or vanilla find. So here we're going to use path compression to accelerate the procedure of solution. So we're going to introduce a path, which is a set. Then we're going to add all the intermediate nodes to the path, result and path and result. So this way, after we exit this while loop, then we have a state that is result equals its parents. Then we're going to redirect all the intermediate node to this result. So basically a for loop for node in path. Then we're going to set their parents to be the result. So next time, if we want to find the root of a given node, it's much faster. So this is the path by path compression. The find by with path compression. So next, let's look at the union function. It will accept two arguments, two cities. Then first, I'm going to check if I1 and I2 are in the same cluster. If so, we do nothing. Otherwise, we do the merge or union. So let's see, R1, let's call this the root R1, R2 equals find I1, find I2. So we're going to check if R1 does not equal to R2. If they are not equal, then we're going to track their rank information and then do the merge. So if recs R1 is greater or equal to that of recs R2, then we're going to set the parents of R2 to be R1, and then we're going to increment the rank of R1 by that of R2. This is one case, and in the other case, we essentially do the same thing, but we reverse the direction. Let's copy these two lines and then do the modifications. We're going to set the parents of R1 equals R2, and then we're going to increment the rank of R2 by that of R1. So that's the full implementation for the find and union methods. So now we are ready to look at the problem logic. In other words, we are going to do the unions for cities. So this is the real work for this problem. As we mentioned, we're going to iterate for city 1, let's see x, in range. So we're going to threshold +1. So this makes sure the common factor will greater than threshold, so up to n, and then that's it. So for y in range, so we're going to start from 2 times x, then ending at n, and with a step x. Then we're going to union these 2 cities, so union xy. So that's all we need to do to make the graph. Finally, we're going to prepare the return for this problem. What we want to return is that for the two nodes or the 2 cities in each of the queries, we're going to check if they are connected by a path. In other words, if they are in the same cluster. So this is actually very straightforward. So we're going to check if they have the same representative or delegate for x, y in queries. So that's it for this solution. I guess let's first do a special case check. Yeah, it passes a special case. Now let's do a generic case check. Oh yeah, it passes the generic case. I guess for this problem, so that's the structure. So we first implemented the find and the union help functions or union find data structures within the solution function. Then we make the connectivity of the cities, and finally we check if 2 cities in each of the query are in the same cluster. In other words, if they are connected. So this is the first part of our plan. The second part of our plan is a temp complexity analysis. So we are going to do a very rough temp complexity analysis. So notice that in this problem, the main work is in part 2, the two for loop. So each of the instance we are going to do a union operation, right? So now let's look at the temp complexity analysis. So first, I'm trying to count how many unions we are doing. So in other words, this is corresponding to the first item here. So the temp on the nested for loop. So we're going to use S to denote the threshold, and the number of total cities is n. So in the inner loop, we are actually iterate with the step x. So basically, we are doing n over x steps, and in the out for loop, we are going to check the threshold value from s plus 1 to n. So this summation is the number of union operations we actually do in the process. Then if we put the n in the denominator outside the summation symbol, we're going to have n times this summation over 1 over x. Then we're going to use a approximation. We're going to use this integral to approximate this summation. So in other words, this is the integral from s plus 1 to n over the integrand 1 over x. So the antiderivative of 1 over x is nothing but logarithm. So then we can get the number of union operations we are doing is actually n times logarithm m minus logarithm s plus 1. So notice that here the logarithm is natural logarithm, but this is okay because we can count temp complexity up to a constant, or we can see we are using big O notation. So this is part 1. So now let's look at part 2. Then we are going to count the whole temp complexity. So we are going to do a analysis that is not very rigorous or not very precise. We are going to count the average temp. So let the amortized temp for union to be alpha n. So here this function alpha n is a slow growing function. So it has a name. It's the inverse Ackermann function. So roughly, if this is the temp complexity for each of the union operation, And then the total temp we're using is n logarithm n minus logarithm s plus 1 times this r of n up to a constant. So that's the full temp complexity for this problem. It's very rough, but if you are interested in knowing the details, so you can check the Wikipedia item for disjoint set data structure. I guess that's about it for this problem. Thank you very much.